Hello, and welcome to the TI Precision Lab introducing SAR ADC power scaling. Precision Labs is a comprehensive online curriculum for analog engineers. More videos can be found by going to ti.com/precisionlabs. Overall, this section will cover the basic ideas of power consumption for the SAR data converter and ways to minimize it. In this video, we will define and explain analog supply power, digital supply power, and front-end driver power. Let's begin by covering the two basic stages of a SAR ADC. First, the acquisition phase is when the SAR ADC allows the input signal to charge the sample and hold capacitor. This happens by closing switch 1 while switch 2 remains open. Next, the SAR ADC will enter the conversion phase. The conversion phase is where the voltage on the sample and hold capacitor is translated into a digital code. The switches swap so that S1 is now open and S2 is now closed. A generic timing diagram is shown with the following signals: chip select, CS, serial clock, S clock, and serial data out, SDO. The acquisition phase is a passive stage where there is very little internal activity for the SAR ADC. All of the conversion and communication happens during the conversion phase. Now let's relate the acquisition and conversion phases to the SAR ADC power consumption. The vast majority of the power consumption comes from the conversion phase. The acquisition phase can be termed as a zero power stage because the power consumption comes only from the quiescent current. The conversion phase is where the SAR ADC will consume power in order to perform both the translation from analog voltage to digital code and the digital communication. The average power, or power per cycle, is the sum of the power consumed in the acquisition phase and the power consumed in the conversion phase divided by the cycle time. It is important to note that by extending the length of the acquisition phase, the average power will decrease since the cycle time will increase. A longer acquisition time will lead to a lower average power. The length of the acquisition period also has important considerations in the selection of the external amplifier driver. In short, a longer acquisition period allows for the selection of a lower bandwidth amplifier driver, which will help reduce system power further. Because understanding the acquisition and conversion period is important for low power design, we will look closely at how these periods are set in different SAR architectures. Note that not all SAR ADCs will support power scaling, so be sure to look in the device datasheet for the curve that shows this relationship. The acquisition and conversion time of a SAR ADC will differ depending on the internal device design. To understand what determines the acquisition and conversion time, look at the timing diagram. First, we will look at the timing for a SAR ADC with an internal conversion clock. With an internal conversion clock, the SAR conversion cycle is always a fixed amount of time. The S clock that the user applies will only influence the speed of the data communication, not the conversion time. In this type of SAR, a lower sampling rate will increase the acquisition time since the conversion time is fixed. The diagrams shown here highlight two different timing configurations for the same device. The configuration at the top is operating at a slower sampling rate than the configuration at the bottom. The transmission rate of the data is independent of the sampling rate. In fact, the maximum communication rate is bounded by the device and the minimum communication rate is only bounded by the total cycle time. Since the conversion time is always fixed, the acquisition time is longer for the slower sampling rate. Two examples of TI SAR ADCs that operate in this manner are the ADS 8881 and the ADS 8332. Note that most precision SAR converters use the internal clock method for setting conversion time. This is because the internal clock will ensure a clean, low jitter clock for the more complex conversion process in a precision SAR converter. Now let's take a look at SAR ADCs with an external conversion clock. For this type of device, the S-clock provided by the user is also used for the conversion cycle. With this method, the conversion time is set to a fixed number of S-clock periods and therefore will expand and shrink with changes in the S-clock frequency. The timing diagrams show the same SAR operating at the same sampling rate but with different S-clock frequencies. It is clear that with a faster S-clock, the acquisition time will increase as shown in the top example. Increasing acquisition time is advantageous because it will allow the input signal more time to settle, which decreases the bandwidth requirement for the front-end driver. Decreasing the bandwidth requirement for the amplifier will result in further power savings. Thus, for the example shown, the top timing diagram is preferable as it will give the maximum settling time to the amplifier. Two examples of TI SAR ADCs that use an external conversion clock are the ADS7042 and the ADS7056. Note that this method of setting the acquisition and conversion rate is typically used in lower resolution SAR converters, for example 8 to 14 bits. As mentioned previously, the higher resolution converters typically use the internal clock to set the conversion time. Not all SAR ADCs will fall into one of these two categories for conversion clocks. For example, devices with an I2C interface will operate very differently from devices with an SPI interface. Some of the I2C devices will have registers that the user writes to in order to set the acquisition time. Also, some of the SPI devices will have a fixed acquisition window. This means the device will only acquire for a fixed number of S-clock periods. The timing diagram shown is for a fixed acquisition type of device. Two examples of TI SAR ADCs with other methods for timing are the ADS7924 and the ADS8321. Note that these exceptions are not common and most devices will fall into one of the first two categories. In regards to the different types of timing diagrams, it is best to always read the device datasheet in order to fully understand how the device will operate and how to determine the acquisition and conversion times. There are three main contributors to the system power of a SAR ADC. First is the analog supply power, abbreviated as AVDD. Second is the digital supply power, abbreviated as DVDD. And lastly is the front-end driver power. These three power consumption contributors will be further explained in terms of how each one is used, as well as how to reduce the power consumption in a system. First, we will look at the analog supply power consumption. The analog supply is used for the internal conversion circuitry of the SAR ADC. The average power consumption for the analog supply will increase as the sampling rate increases. This is due to the fact that as sampling rate increases, the acquisition time decreases, which results in more frequent conversion phases. The datasheet supply current versus throughput graph for the ADS7042 is shown, and the linear relationship is clearly visible. In order to reduce a system's power consumption, lowering the sampling rate to the lowest acceptable throughput for the application will decrease the average analog supply power consumption. Using the datasheet's supply current versus throughput graph, let's calculate the AVDD supply power consumption. For this example, the device is running at 600 kilosamples per second. On the graph, we see a typical supply current for 600 kilosamples per second is 120 microamps. With a 3.3 volt AVDD, the analog supply power for this device is 396 microwatts. Note that with some devices, there will be an additional source of power consumption on the reference pin. This can be calculated in the same way as the AVDD supply power and considered as an additional source. Next, we will look at the digital supply power consumption. The digital supply for a SAR ADC is only used for the digital communication circuitry of the device. This means that the digital supply power consumption is related only to the SPI or I2C output. For a SAR device with SPI communication, the power is only consumed on the digital supply for the serial data output line, or SDO, and not for the chip select, serial data input, or system clock lines, since those are all powered by the master. The power consumption is a function of the DVDD voltage, sampling rate, digital output code, and capacitance. The capacitance is comprised of the SDO trace, the SDO pins on both the ADC and the master, and any external capacitors added to the SDO line. The equation to estimate the average digital supply current is given as the capacitance multiplied by the DVDD voltage multiplied by the frequency of transitions on the SDO output. More output transitions from low to high or high to low on the SDO line will result in more current draw. The worst case scenario from a current draw perspective is if every other bit on the SDO output alternates. The maximum number of SDO transitions for a 12-bit SAR ADC is shown in the timing diagram graphic on the right. Since we now understand the factors that play into the digital supply power consumption, let's look at methods to reduce this power. First, since the digital power is a function of DVDD, lowering the DVDD voltage will allow for a lower digital supply power consumption. If the system can operate with a 1.8 volt logic level, then switching from a 3.3 volt DVDD to 1.8 volt DVDD will drastically decrease power consumption. Next, digital supply power consumption is proportional to throughput. By running the SAR at the lowest possible sampling rate, the average digital supply power consumption will decrease, because the frequency of SDO transitions will also decrease. Lastly, reducing the trace capacitance of the SDO line on the printed circuit board, or PCB, will decrease power consumption. Shorter traces will have less capacitance. TI's Analog Engineer's Calculator has a built-in tool to calculate trace capacitance by entering the characteristics of the PCB and the trace of interest. A link to this tool is provided at the bottom of the slide. Let's walk through a digital supply power consumption example calculation. Using the equation for DVDD current, we will need the DVDD voltage, capacitance of the SDO line, and the frequency of SDO transitions. First, the DVDD voltage is easy to determine, since it will be the voltage that is supplied to the part. In this example, we are using 3.3 volts. The pin capacitance is usually available in a device datasheet, or it can be estimated as 3 picofarads. Next, the trace capacitance can be calculated using the Analog Engineer's Calculator by entering in your PCB characteristics, trace length, and trace width. By entering these values into the calculator, we determine the SDO trace capacitance to be 1.322 picofarads. Lastly, we need to figure out the frequency of SDO transitions. For this example, we have a 12-bit output, and with 12 bits, the worst-case scenario would be for the SDO line to transition on each bit, resulting in 12 SDO transitions. The frequency of SDO transitions is determined by taking the number of transitions and dividing it by time. Since the device is operating at 1 megasample per second, the cycle time is 1 microsecond. To find the DVDD supply power, we simply multiply the DVDD current by the DVDD voltage. Entering these values into the equation will give us an estimated DVDD supply power of 956.8 microwatts. Moving on to the third contributor to SAR ADC power consumption, we will now focus on the front-end driver. Typically, an operational amplifier, or op-amp, is used to drive the input of the SAR ADC. This amplifier consumes power due to the quiescent current of the op-amp and the op-amp power supplies. Choosing an op-amp to drive the SAR ADC is described in detail in the SAR ADC Input Driver Design Precision Labs videos. These videos describe how to determine the bandwidth required for the front-end driver. The bandwidth required depends on the throughput of the SAR ADC. At lower throughput, less bandwidth is needed to drive the SAR. Generally with op-amps, as the bandwidth specification decreases, the quiescent current, or IQ, also decreases. The chart in the bottom left shows some example amplifiers comparing the bandwidth and quiescent current. In order to minimize front-end driver power consumption, operating the SAR at a lower sampling rate will allow for a lower bandwidth op-amp to be used, which in turn will have less quiescent current. Note that the power is calculated by multiplying the total supply voltage by the quiescent current. The front-end driver power consumption will decrease with a lower quiescent current op-amp. The TI Precision Labs op-amp series has a video series explaining op-amp bandwidth in depth. Going to a lower-powered front-end driver does not come without a cost. As op-amp quiescent current decreases, the intrinsic noise of the op-amp increases at a proportional rate of 1 over square root of IQ. This is important to keep in mind because there is a trade-off between power and noise. So depending on what is important in your system, the amplifier should be selected appropriately. Next, the feedback resistors of an op-amp circuit will result in additional power consumption. Sometimes, in order to reduce power consumption, people will use large-valued resistors in order to decrease the load current, but resistor noise increases with resistance. A good rule of thumb is to keep the op-amp intrinsic noise dominant compared to the resistor noise from the feedback network. The TI Precision Labs op-amp series also has a video series dedicated to noise that goes into much more detail on this topic. Also, as an amplifier's quiescent current decreases, typically the slew rate will also decrease. While most applications require a front-end driver for the SAR ADC, in some cases the circuit can be designed without the driver. This applies to low-frequency voltage inputs that the user can connect directly to the input of the SAR ADC, as shown in the schematics on the left. This topology is effective only for low sampling rates, and there is a TI tech note showing a specific example of this topology with accurate measurements for 20 kilosamples per second and lower. The link for this is shown at the bottom of the slide. The main advantage to not using a driver amplifier is the power savings. The graph shows a measured example of system power, and it is clear that the op-amp is about 50% of the total power. On this slide, an example of measured results for power scaling is shown. For this example, the system used an ADS 7042 with an AVDD of 3.3 volts, a DVDD of 3.3 volts, an op-amp power supply of 4.5 volts, and different op-amps for each sampling rate. Different op-amps were used because the bandwidth requirement changes with sampling rate. The table allows you to see 3 different power levels, the amplifier used, and the sampling rate. The power is broken down into the 3 contributors that were explained earlier in this video: front-end driver power, analog supply power, and digital supply power. The last column combines the 3 power components to give a total system power. The power scaling is shown in the graph, and the difference between 1 kilosample per second, 100 kilosamples per second, and 1 megasample per second is clear and drastic. If we zoom in on the 1 kilosample per second power measurements, you can now see the 3 contributors on a smaller y-axis scale. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.